For years, while searching for life in the universe, we always had one target: to find a planet that was an exact copy of Earth, rocky, at the right distance from the right star. We were searching for the only formula for life we knew. But we were catastrophically wrong. Because the James Webb Telescope looked at a planet 120 light-years away from us, a planet 8.6 times more massive than our own. And what it found challenged the very laws of physics. In its atmosphere, there was a molecule that can only be produced by living things. This was not a mistake. The margin for error was less than 3 in 1,000, which means 99.7% certain proof. But the real shock was that this planet, Sex, could be even more habitable than Earth. If you too get excited by feeling just how small our place in the universe is, then like this video and subscribe to the channel. Because in a moment, all your beliefs will be shattered. Are you ready? Let's begin. For years, our search for life had a single target: to find the twin of Earth. We searched for a rocky planet, orbiting a star like the Sun, at just the right distance. Because we believed this was the recipe for life: oxygen, water, and a familiar gravity. But the James Webb Space Telescope looked into the depths of the Leo constellation, 120 light-years away. And in that moment, everything changed, because what it found was not a twin. It was a world far stranger, far larger, and potentially even more habitable than Earth. What this discovery demolished all our prejudices about the class of planets known as super-Earths. This planet, designated K2-18 Biggie parts, is unlike anything we know, because it possesses a mass exactly 8.6 times that of Earth. This colossal size makes it smaller than a gas giant like Neptune, but far larger than a rocky planet like Earth. This was a revolution in the search for life, because until just yesterday, we saw planets of this type as uninhabitable balls of gas, too big, Marcel, too heavy, too crushing to support life. But K2-18 B exactly shattered that theory. The gravitational pull on this planet's surface is nearly 3 times that of Earth's, meaning a person weighing 68 kilograms here would feel heavier than 180 kilograms there. This crushing weight seems like a disadvantage at first, but the real secret is hidden right here, because this intense gravity holds the planet's atmosphere in an iron grip. It prevents the atmosphere from escaping into space, like what happened to Mars billions of years ago. For this reason, K2-18b can preserve one of the most fundamental requirements for life, a stable atmosphere, for trillions of years. This forces us to ask the question, maybe the best place for life isn't a copy of Earth, but this giant cousin of ours. But it's not just its size that makes this planet truly different, because Webb's measurements showed an almost unbelievable stability on the planet's surface. The temperature across the entire planet hovers at a constant 49 degrees Celsius. This figure, roughly 120 Fahrenheit, is not a coincidence. It is a magical setting for life. It's not too cold, so water doesn't freeze. It's not too hot, so water doesn't evaporate and disappear. This is that perfect Goldilocks range, where water can remain in its liquid state. This planet orbits its star, a red dwarf, in just 33 days, a very close orbit. But because its star is cooler than the Sun, the planet receives almost the same amount of energy per square meter as Earth. This cosmic coincidence allows this world 120 light-years away. to exist in the same thermal environment as our own. For this reason, HAL K2-18b is like a perfectly regulated hot spring on a planetary scale. On Earth, we experience massive temperature differences between the poles, the equator, night and day. This forces living things into a constant struggle for survival. But on K2-18b, the situation is different. Because its thick, child hydrogen-rich atmosphere distributes heat so efficiently to every corner of the planet that even the night side, which never sees the sun, remains warm enough to support liquid water. This means a paradise environment, where life can grow and thrive, of course, without having to expend energy. Yet all these features pale in comparison to the one molecule scientists saw, because Webb detected a molecule in the planet's atmosphere called dimethyl sulfide. This chemical is unlike anything you've ever heard of, because, on Earth, this molecule is not produced by any known geological or non-living process. It is produced only and exclusively by living organisms. The phytoplankton in our oceans release this gas into the atmosphere as a byproduct of their metabolism. Some species of bacteria and algae do the same. For this reason, dimethyl sulfide is a biosignature. In other words, the chemical fingerprint of life. Finding it in an alien atmosphere is like finding a flashing neon sign that says, "Life is here." The confidence level of this discovery is what's truly shocking. Because scientists are 99.7% certain that the signal is real. This is a statistical gold standard known as a 3 sigma detection, meaning the probability of this signal being an error or noise is less than 3 in 1,000. This is the same level of confidence used in particle physics to confirm new subatomic particles. So, this is not just a hint. This is the strongest evidence for life in human history. In short, here's what we have. A giant planet of a type we once thought was uninhabitable. A perfect temperature of 49 degrees across its entire surface, and the 99.7% certain proof of a chemical, produced only by living beings. When all these pieces come together, they mean one thing: we are not alone. But the real story is just beginning. Because the secrets of this planet are not limited to the gases in its atmosphere. The combination of these conditions points to the existence of something on its surface we can't even imagine. The planet's hydrogen-filled atmosphere combines with the surface water to create an ocean unlike anything we know. An ocean where the pressure would instantly crush any form of terrestrial life, but which could also be the most favorable environment for life in the universe. So how is this possible? What exactly is this hydrogen ocean? And what kind of life could it harbor? The answer lies in the planet's chemistry and physics. So because this world fundamentally changes the way water and atmosphere interact, and this turns it into something we have never seen before. A hydrogen ocean. This is fundamentally different from the water oceans we know, because under the crushing pressure on the surface of K2-18, the hydrogen gas in the atmosphere dissolves into the liquid water, just like the carbon dioxide in a soda. This completely changes the chemistry of the water. This hydrogen-enriched water can remain liquid over a much wider range of temperatures and pressures than pure water. For this reason, it can exist in a liquid state from near 0 degrees to 149 degrees Celsius. This offers a massive playground for life to develop. But the real revolution is about pressure. Because in the deepest parts of Earth's oceans, the pressure is nearly 1,000 times that on the surface. This would instantly crush the cellular structures of most life forms. Yet, in the hydrogen ocean of K2-18, the dissolved hydrogen acts as a natural pressure buffer. This allows the pressure to remain at levels that permit life to exist, even at much greater depths. Perhaps most importantly, this ocean also protects the planet's atmosphere, because Earth's atmosphere is slowly leaking into space. But on K2-18b, the hydrogen escaping from the atmosphere is replaced by new hydrogen evaporating from the ocean. This means a giant reservoir that could keep the planet's atmosphere stable for trillions of years. For this reason, life here not only can emerge, but it could also have an almost infinite amount of time to evolve. This situation also brings with it the possibility that life can breathe hydrogen. This means a completely alien biochemistry. Yet, the real reason this planet and its ocean can remain stable for so long is its star itself. Because K2-18 is not a star like our Sun. It is a red dwarf. These small, cool stars, which make up about 75% of the stars in our galaxy, are the most frugal power plants in the universe. Our Sun has a lifespan of about 10 billion years. It will eventually turn into a red giant and destroy all life on Earth. But red dwarfs burn their nuclear fuel so slowly that they can shine for up to 10 trillion years. This is hundreds of times longer than the current age of the universe. This incredible longevity has profound implications for life, because, on Earth, it took complex life about 4 billion years to evolve from simple bacteria to today's ecosystems. If life on K2-18b has had even a fraction of that time, it could have reached levels of complexity that would make Earth's biosphere look primitive. Red dwarfs can often be dangerous, because some produce powerful flares that can sterilize planetary surfaces. But Hashkos K2-18 seems to be a well-behaved red dwarf. So, it allows its planet to maintain a stable atmosphere and sustain life. This endless stability creates the perfect environment for life to reach a complexity beyond our imagination. However, the chemistry of this alien world makes the story even stranger. Because Webb didn't just find dimethyl sulfide in the planet's atmosphere, it also detected large amounts of methane and carbon dioxide. The presence of these gases together points to an active planetary metabolism. But the truly mind-bending possibility arises from the extreme pressure at certain layers of the planet. Because, at the right altitude, the pressure and temperature in the atmosphere create the perfect conditions to compress carbon atoms into crystalline diamonds. These microscopic diamonds form in the upper layers of the atmosphere and rain down toward the surface. So, yes, it may be raining diamonds on this planet, as magical as this may seem to us. For the life forms there, it might be as common as raindrops are for us. Even more interesting is a molecule that was not found in the atmosphere: ammonia. If this planet were a lifeless gas giant, its atmosphere should have contained abundant ammonia. Yet, the absence of ammonia provides strong evidence that biological processes are actively removing it from the atmosphere. Life on this world is not just existing, it is actively shaping the chemistry of its planet. In conclusion, the picture becomes clear. A planet 8.6 times more massive than Earth, with stronger gravity, a perfect, constant temperature of 49 degrees on its surface, a massive, hard-sea stable ocean where hydrogen mixes with water, and an immortal star that will provide energy for all of this for trillions of years. On top of that, diamonds rain from its atmosphere and chemicals that are the fingerprint of life are present. We are no longer asking, so is there life elsewhere? We are now wondering, what does that life look like? But let's put all these theories and possibilities aside. The technology behind these discoveries is as revolutionary as the discoveries themselves. So, how are we able to detect a few atoms in the atmosphere of a planet 120 light-years, about 1.1 quadrillion kilometers, away from us? The telescope that achieved this is not just an observation tool, because it is also a time machine that allows us to look into the past. But that time machine, on that Tuesday morning in December, when it downloaded the most shocking data in human history, everything stopped. Because Niku Madhusudan, sitting at his computer at Cambridge University, looked at the spectrum of that infrared light that had travelled for 120 light-years, until what he saw was enough to make his hands tremble. Because there was something in that data that shouldn't have been there, an impossible signal, the fingerprint of life. That signal was dimethyl sulfide. It wasn't just a trace, it was strong, so intense that the probability of it being a mistake was less than 3 in 1,000. Scientists call this level of certainty a 3 sigma detection. This is the statistical threshold used to confirm the existence of gravitational waves or to discover new subatomic particles. So, it was not a possibility, it was a fact. The presence of this molecule there seemed physically impossible, because on Earth, no known geological process, no lifeless chemical reaction produces this molecule. It is made only and exclusively by living things. For this reason, finding dimethyl sulfide in the atmosphere of planet K, 218 E3P House 120 light-years away, Seki was like hanging a neon sign in the middle of the universe that read, "Life is here." Niku Madhusudan and his team had been studying this world for months. They were using the incredible sensitivity of James Webb. But this was the moment that changed everything, because this finding could mean the end of humanity's cosmic loneliness. We might no longer be alone in the universe. This possibility was no longer just a theory, because this was a statistical certainty of 99.7%. But this wasn't the only anomaly Webb found, because the planet's temperature was also impossible. The telescope determined that the entire surface of K218, B Chatsir, without exception, was at a constant 49 degrees Celsius, or 120 Fahrenheit. But this was an unbelievable situation. The planet is tidally locked to its star. This means one face constantly looks at the star, while the other face should be in eternal darkness and cold. The day side should have been scorching, and the night side should have been freezing. But it wasn't, because the planet's thick hydrogen atmosphere distributed the heat so perfectly that the entire planet stayed at a single, comfortable temperature. This is a situation unprecedented on Earth. This temperature of 49 degrees was equivalent to a hot summer day in Death Valley, a relaxing bath, or the fever of a human body fighting an infection. It was a perfect setting for life, because it allowed water neither to freeze nor to evaporate. This situation showed that the planet was not just habitable, but potentially more hospitable than Earth. Because life here would not have to struggle with extreme temperature changes. And now comes the real shock. Because sometimes the biggest discovery is not in what you find, but in what you don't find. Webb's spectral analyses showed that there was abundant methane in the planet's atmosphere. Methane, on Earth, is largely a product of biological activity. But it is also a highly reactive molecule that breaks down in just decades under ultraviolet radiation. So, the continuous presence of abundant methane in the atmosphere meant that something was producing it in massive quantities. This, in itself, could have been proof of life. But the real proof was something that wasn't there. Ammonia. If K2-18b were a lifeless gas giant, its atmosphere would be expected to have abundant ammonia. Yet, Webb detected almost no ammonia. This could mean only one thing. Biological processes on the planet were actively consuming ammonia, cleaning it from the atmosphere. This was a state of chemical disequilibrium. And this disequilibrium is one of the strongest signs that a planet has a living metabolism. Life on this world isn't just breathing, it is actively reshaping the planet's chemistry. In short, the evidence was piling up. A molecule produced only by life. An impossibly stable and perfect temperature reigning over the entire planet. And a continuous chemical imbalance, governed by an active biosphere. Each finding was revolutionary on its own. But when they all came together, they pointed to an irresistible conclusion. But all this evidence brings us to a single mind-boggling question. How does the technology that delivered this data to us work? Because detecting a few molecules in the atmosphere of a planet 120 light-years away is not like looking for a needle in a haystack. And this pattern led us to one of the most chaotic places in the universe, a stellar nursery, because Webb looked not only at mature worlds, but also at a young star named Scientlii, where planets are still being born. And there, it found something that shouldn't have been there again. A gap, millions of kilometers of nothingness. This discovery revealed a truth that could overshadow even the findings of K2-18 EED, because we were witnessing the birth moments of the universe. This gap was a mystery. See, Scientlii is a baby star, only 6 million years old. For this reason, it's surrounded by a giant debris disk where planets are forming. This disk of dust, ice, and rock fragments is a cosmic construction site. But when Webb looked at this disk, it saw a giant hole in the middle, a region millions of kilometers wide, almost completely cleared out. This gap shouldn't have been there, because, according to the laws of physics, this debris should have been spread throughout the disk. Previous telescopes had noticed this gap, but they couldn't explain it. Magnetic fields or pressure waves could not create such a clean gap. Something, like a giant cosmic vacuum cleaner, must have cleared all the material in its orbit. But that something was invisible, until Webb's infrared eye focused inside that gap. There, it was hiding. The heat signature of a planet, too faint to be seen with the naked eye, but warm enough for Webb to see. This was a brand new way of finding planets. We no longer had to wait for them to pass in front of their stars to see them. We could just look for the gaps they create, their cosmic fingerprints. But the real shock in the Scientlii system, was the planet itself. Because this newly discovered world broke the record for the lightest planet ever directly imaged. This was an impossible achievement. This planet has only 1/3 the mass of Jupiter, All previously directly imaged planets were giants with many times Jupiter's mass. Because, only these super-Jupiters were bright and hot enough to be seen despite the dazzling glare of their stars. This new world, however, was a full 10 times less massive than any previously imaged planet. And this made detecting it almost impossible. So because the light coming from this planet was about 10 billion times fainter than the light of its own star. This was like trying to see a single candle placed next to a stadium's brightest projectors. With a telescope from the other side of the country. For this reason, Webb's ability to distinguish such a faint object was a triumph that pushed the boundaries of engineering. And its temperature? That magic number again. About 49 degrees Celsius. This showed that the planet was not a gas giant, but had a thin enough atmosphere to potentially support life. Yet, the greatest discovery was not a single planet or a single gap, because, as Webb continued its investigation, a dizzying pattern began to emerge. Our galaxy was not a giant desert dotted with a few rare oases. It was teeming with life. Within a small sphere of just 200 light-years around Earth, astronomers have already identified more than 50 planets showing signs of habitability. And this number is growing every day. Super-Earths like K2-18b, smaller rocky planets orbiting red dwarfs, worlds completely covered in ice, but which could harbor vast oceans beneath their surfaces. Each of these represents a different experiment of evolution, and the statistics are mind-boggling. If there are more than 50 potential life-harboring worlds in just our tiny neighborhood, there could be billions of living worlds in the entire Milky Way galaxy, which hosts 400 billion stars. Perhaps there are more living planets in the galaxy than there are people on Earth. For this reason, the question is no longer, are we alone? The question is, how many neighbors do we have? A world born in a gap, a record-breakingly light planet that shouldn't have been seen, and billions of potential homes for life scattered throughout the entire galaxy. These findings have fundamentally shaken our understanding of the universe. But all these discoveries make one question even more important. How? How does the James Webb Space Telescope accomplish all this? How does it see the candle next to the stadium light? How does it perform a chemical analysis of an atmosphere 120 light-years away? The answer to these questions lies in the telescope itself, in its revolutionary technology. Because Webb is not just a telescope, it is a set of incredibly sensitive instruments designed to see the universe as never before. And at the heart of these instruments lies Webb's greatest secret, a technology that not only collects light but can also bend and block it. A system of mirrors and masks that works like a cosmic magician. This system, so how does this cosmic magician work? What is the secret behind all these seemingly impossible discoveries? Now, let's step away from the shocking findings for a moment and try to understand the engine of this revolution. The James Webb Space Telescope itself. Because this telescope is not just a big pair of binoculars. It is a multi-layered engineering marvel, designed to solve the most fundamental secrets of the universe, with unbelievable precision. Now, let's dive into the technical details of that marvel. It all starts with what Webb sees, or rather, what it doesn't see. Because Webb is not concerned with the visible light that the human eye sees. Its specialty is infrared light, heat, the language of heat. This makes a fundamental difference in understanding the universe. Because, as the universe expands, the light from the most distant galaxies is stretched like a rubber band, and its wavelength gets longer. For this reason, light that started its journey billions of years ago as blue or white is no longer in the visible spectrum when it reaches us, but in the infrared. If you want to see the birth moments of the universe, you need to see in infrared. But to capture this heat, you need a giant eye. This is where Webb's 6.5-meter primary mirror comes in. This massive structure, almost 3 times wider than Hubble's 2.4-meter mirror, is not a single piece. It is composed of 18 hexagonal segments, each coated with a microscopic layer of gold, working in perfect harmony. The choice of gold is not a coincidence, because Schätzer gold is one of the most efficient materials in the universe for reflecting infrared light. The alignment of these 18 segments is so precise that the telescope has the theoretical power to detect the heat radiated by a bumblebee on the surface of the Moon. This represents a light gathering and focusing capacity that no telescope has ever achieved before. So, Webb can see not only farther, but also fainter and colder. But seeing the infrared universe brings a huge problem: noise. Because heat is infrared light itself. If the telescope itself is warm, its own heat would completely overwhelm the faint signals from billions of light years away that it is trying to observe. This is like trying to hear a whisper in a stormy sea. For this reason, one of Webb's most critical engineering marvels is its giant sun shield. This is not a simple shield. It is a sophisticated cooling system, the size of a tennis court, consisting of 5 layers. The telescope is located in a special orbit 1.5 million kilometers from Earth, called the L2 Lagrange point. At this point, the Sun, Earth, and Moon always remain in the same direction. This allows Webb to keep its massive shield constantly facing these 3 heat sources. The 5 layers, made of a special material called Kapton, reflect heat back into space thanks to the vacuum gaps between them. Each layer is colder than the one before it. This system is so effective that while the sun-facing side of the shield reaches about 85 degrees Celsius, the shaded side where the telescope's instruments are located is kept at a freezing cold of minus 233 degrees Celsius. This is even colder than the surface of Pluto. This extreme cooling almost completely eliminates the telescope's own thermal noise. So, Webb can remain quiet enough to hear even the faintest, oldest whispers of the universe. So how does this ultra-sensitive and ultra-cold eye read the chemicals in a planet's atmosphere? The answer lies in an ingenious technique called transit spectroscopy. You can think of this technique as a cosmic barcode reader that uses its star as a backlight. When a planet like K218b passes in front of its star, a very small portion of the starlight filters through the planet's atmosphere to reach us. This is where the magic begins. Because every molecule in the atmosphere absorbs light at its own specific wavelengths, just like a sponge absorbs water. For example, water molecules absorb certain infrared colors, while methane molecules absorb other colors. Webb's device, called a spectrograph, separates this filtered starlight into its constituent colors like a prism. In this color spectrum, dark lines, or absorption lines, appear where the light has been absorbed by specific molecules. The pattern of these dark lines is a unique fingerprint that shows which chemicals are present in that atmosphere. The discovery of dimethyl sulfide or methane was made possible by reading these fingerprints. This is a method so sensitive that it can detect concentrations as small as a few particles per billion. However, the biggest obstacle to this method is an incredible difference in brightness. The light filtered through a planet's atmosphere is so faint compared to the star's own light that this difference is measured as 1 in billions. This is the problem of seeing a firefly next to a projector we mentioned earlier. One of the weapons Webb uses to solve this problem is coronagraphy. This device is a small, shaggy, precisely designed mask placed inside the telescope. This mask blocks the direct light from the star, just like an artificial solar eclipse. This allows the much fainter light of the planet or the debris disk around the star to emerge. But even this is not enough, because the slightest imperfections in the telescope's optics create false light spots called speckles that can mimic planets. This is where Webb's most advanced weapon comes into play: artificial intelligence-powered image processing algorithms. These algorithms analyze the raw data and systematically remove the star's glare and all other noise. This process is similar to digitally filtering the noise of a jet engine to hear a whisper underneath. For this reason, the secrets of K218b or the C Antlier system were solved not only with the telescope's hardware, but also with this incredible software power. A giant gold-coated mirror, a tennis court-sized cooler, a cosmic barcode reader, and an AI-powered image cleaner. Webb's power comes from the individual excellence of each of these systems and their flawless harmony. But this is just the visible surface. There is another technology used to make sense of the terabytes of data produced by these systems. Statistical analysis methods that scientists use to find invisible patterns, how diving deep into the data. And these methods tell us not only what exists, but also how real a finding is. This brings us to the mathematics behind that magical 99.7% figure. That is, and this brings us to the mathematics behind that magical 99.7% figure. The statistical beast called sigma detection. This mechanism is the most reliable way to determine whether a signal is a real discovery or just random noise. You can think of this process like flipping a coin thousands of times. A single toss has a 50% chance of being heads. But the probability of 997 out of 1,000 tosses being heads is so low that for it to happen by chance is impossible within the age of the universe. This is precisely the level of confidence scientists have in the dimethyl sulfide signal on K218b. In physics and astronomy, sigma is a unit of standard deviation that measures how much a signal deviates from random fluctuations. A certain sigma threshold is usually required to confirm a discovery. For example, a 1 sigma detection says a signal is 68% likely to be real, which is quite weak confidence. When you reach the 3 sigma level, this ratio jumps to 99.7%. This means the probability of the signal being a false alarm is only 3 in 10,000, the greatest breakthroughs in modern science, such as the discovery of the Higgs boson or the confirmation of gravitational waves, were generally announced after passing the 5 sigma 99.99994% confidence threshold. Webb's achievement of a 3 sigma level for the dimethyl sulfide detection is therefore revolutionary, because this is the highest statistical confidence ever obtained for a biosignature in an exoplanet's atmosphere. To reach this conclusion, multiple independent observations were made. Webb's different instruments repeatedly confirmed the same molecular fingerprint at different wavelengths. This increased the reliability of the discovery manifold, because it eliminated the possibility of it being an error of a single instrument. This is why the 99.7% confidence is not just a number. It is irrefutable proof that has passed through science's most rigorous verification processes. But Webb has another, much more direct, much more daring method in its arsenal for finding planets. Direct imaging. This is, as the name suggests, taking a photograph of an exoplanet. While this sounds simple, it is one of the most technically challenging methods, because a star is billions of times brighter than the planet orbiting it. This is like trying to see a single candle standing next to a stadium's projectors from one end of the country to the other, as we mentioned before. Previous telescopes like Hubble could typically directly image massive super-Jupiter planets, several times larger than Jupiter, because these giants, being young and hot, shone brightly in the infrared. But Webb broke new ground in this area with its discovery in the C. Antilles system. The telescope managed to directly image a planet with only 1/3 the mass of Jupiter. This was 10 times lighter than the lightest planet previously imaged. To achieve this, a tremendously complex process was used, combining the coronagraphy technique mentioned in Section 3A with artificial intelligence, while Webb blocked the star's light with a mask. Advanced algorithms cleaned up the false light artifacts called speckles caused by the telescope's optics in real time. This required the telescope to both hold its position with the precision of hitting a coin on the moon with a laser, and incredible processing power. The significance of this achievement is immense, because it means that Webb can now directly see not only giant gas planets, but also smaller, potentially rocky worlds, much more similar to the planets in our solar system. Yet, Webb's most underappreciated but perhaps most important ability is its capacity to see the invisible. That is, to find a planet based on the gap its existence creates. The discovery of the C. Antilles star system happened exactly this way. This young star is surrounded by a massive ring of dust and rock left over from planet formation, called a debris disk. When astronomers looked at this disk, they saw that it consisted of 3 distinct rings, and between these rings were suspiciously clean gaps, millions of kilometers wide. These gaps shouldn't have been there, because the natural structure of the disk would suggest a more homogeneous distribution of material. Something like a cosmic vacuum cleaner had cleared these orbits. When Webb turned its infrared eye to one of these gaps, it found a faint heat source glowing within that nothingness. This was a young planet, the mass of Saturn, that had cleared all the material in its orbit, creating that gap. This was a completely new method for finding planets. We no longer have to wait for a planet to pass in front of its star. We can find them based on the fingerprints they leave behind, the gaps they create. This technique, by allowing us to discover countless planets that never pass in front of their stars from our perspective, multiplies the number of potential worlds that can be found, improving a signal's reality with sigma detection, photographing planets smaller than ever seen before with direct imaging, and revealing invisible worlds by analyzing gaps in debris disks. Webb's arsenal consists of interconnected and incredibly powerful tools, designed to understand the universe. Thanks to these techniques, we can now see not only what exists, but also what should exist but doesn't. We can measure not just a planet, but its effect on the entire system. But what's truly exciting is the grand story all these techniques tell us when they come together. Because these tools don't just tell us there's a planet there, they tell us that planet's chemistry, or temperature, mass, age, and even potentially its biology. This is no longer just connecting the dots. This is starting to see the living picture behind those dots. And that picture tells us that worlds like K2-18b are not just habitable, but also much more different, much more surprising, and perhaps much more. And that picture shows us that worlds like K2-18b are not just habitable, but also much more different, much more surprising, and perhaps much more superior than our own. But now we come to the true climax. Because Webb's discoveries are not limited to a single planet. This telescope has started a cosmic revolution. It has revealed mind-bending findings in every corner of the galaxy, overturning all known theories. The tempo increases, heartbeats quicken. Because we are now going to the moments when the greatest discoveries in human history were made. It was impossible. But it was real. Webb saw it. The scientific world was fundamentally shaken. Because the mass of K2-18b was in a place it shouldn't have been. A full 8.6 Earth masses. This number alone demolished everything we knew about how habitable a planet could be. Because this makes it a super Earth. But at the same time, it places it right on the threshold of being a mini Neptune. This line means everything for life. Because on one side of this line, there are rocky worlds with a surface. On the other side, there are crushing gas giants with no surface. For years, we believed that any planet heavier than 8 Earth masses would inevitably become a gas giant. Their atmospheres would be so heavy that the existence of liquid water on the surface would become impossible. But SETI 2-18G shattered this theory to pieces. It was not a gas giant, but it was a water world. This was the first time in history that we had evidence of such a massive planet with such a high potential for harboring life. This enormous mass gave it a gravitational pull nearly 3 times that of Earth. This meant it could protect its atmosphere for billions, even trillions of years. Mars died because it lost its atmosphere. But the immense mass of K2-18 protected it from this fate forever. Scientists were in shock because this completely changed the parameters of the search for habitable planets. We were no longer searching for Earth's twin. Perhaps what we should be looking for was this giant, more powerful, and more stable cousin of Earth. But there was something bigger, something more shocking. So because that chemical cocktail in the planet's atmosphere was the clearest evidence of a planetary biology. Dimethyl sulfide, methane, carbon dioxide, and the absence of ammonia. These 4 findings were exciting even individually. But together, like a symphony, they played the melody of a living world. The atmosphere was in a state of deep chemical disequilibrium. What does this mean? In a lifeless atmosphere, chemicals eventually reach an equilibrium. The reacting molecules are depleted, and a static mixture remains. But in the atmosphere of K2-18, methane and other gases that should have reacted with each other and disappeared were found in abundance. This could mean only one thing. Something was continuously pumping these gases into the atmosphere, and just as life on Earth maintains the balance of oxygen and methane, this was evidence of a metabolism on a planetary scale. the breathing of a biosphere. The 99.7% certainty of dimethyl sulfide was the brightest jewel at the center of this picture. But the abundance of methane and the absence of ammonia were the vital pieces that completed this image. This was the first time in history we had such a strong, multi-layered line of evidence that an exoplanet's atmosphere was being actively shaped by biological processes. This wasn't just saying there might be life there. This was saying life there is changing the chemistry of the entire planet. And now, we go back to where it all began. The temperature, 49 degrees Celsius. This number, Shastis, might be the biggest miracle in this story, because this temperature is too perfect to be a coincidence. K 2-18b orbits very close to its star. It completes a tour in just 33 days. This is even closer than Mercury's orbit around the Sun. Normally, a planet this close should have been scorched and turned into a hellscape. But it wasn't, because its star was a red dwarf. It was much cooler and fainter than the Sun. The combination of these two factors, a close orbit and a cool star, made the amount of energy K2-18 Pb receives per square meter almost identical to the energy Earth receives from the Sun. This cosmic lottery was a miracle in itself, but what was truly incredible was that this temperature remained constant all over the planet. It has a tidally locked rotation. One side is constantly bright. The other side is constantly dark, and therefore, the day side was expected to be scorching, and the night side was expected to be frozen. But Webb's data showed that the planet's thick hydrogen atmosphere distributed heat so efficiently that there was almost no temperature difference between the day and night sides. This meant a planet with a global thermostat. This was a natural engineering marvel that seemed designed for life in the universe. And this was the first time in history that such a stable and homogeneous global climate had been proven on an exoplanet. Yet, the biggest shock perhaps came from the most unexpected place, from the C Antliae system, because when Webb looked there, it didn't see a mature planet like K2-18b. It saw a baby, a planetary system still in its formation. Stage only 6 million years old, and inside that system's debris disk, it found a planet candidate, the massive Saturn, with a surface temperature of again 49 degrees. This finding changed everything, because it showed that conditions suitable for life could emerge even in the chaotic and violent moments of planetary birth. A planet didn't have to wait billions of years to become habitable. Perhaps life was born along with the planet. The three-ringed debris disk around C Antliae was like a textbook showing the different stages of planet formation. And in one of those gaps, that faint glow, the evidence of a planet's existence, showed us how planets shaped their systems. But, most importantly, was that even this young planet had that magical temperature of 49 degrees. This implied that this temperature might not be a coincidence in the universe, but perhaps a fundamental set point on the path to habitability. This was the first time in history that habitable conditions had been detected on a planet in its formation stage. And this was the strongest evidence that new cradles of life might be being born right now. All across the galaxy, a giant mass, a living chemistry, a perfect temperature, and the moment of life's birth. These four epic discoveries, Alachi, when brought together, changed our view of the universe forever. We now see not just distant worlds, but their inner workings, their chemistry, and their potential biology. We are not just finding a planet, we are uncovering the potential of an ecosystem. But all these findings bring us to an even deeper question. Is the story of K2-18 unique in this universe? Or is this just the beginning? The data Webb has collected so far shows that similar worlds may exist in every corner of our galaxy, and the diversity of these worlds pushes the limits of our imagination. Because Webb didn't just find a planet, it opened the door to a new universe of possibilities. And behind that door, there wasn't just K2-18RB, there was a whole galaxy full of living worlds. Because Webb's revolution was not limited to a single planet. It was a statistical explosion. The telescope within a small sphere of just 200 light-years around Earth detected more than 50 potentially habitable planets. More than 50. This number alone created an earthquake. But because this meant that every corner of our galaxy was filled with life-bearing worlds. This was not an exception. This was a rule. The universe, loves life. This is not an exaggeration. This is mathematics itself. If there are more than 50 candidates in just our tiny local neighborhood, a cosmic stone's throw of 200 light-years, then how many worlds could there be in the entire Milky Way galaxy? 400 billion stars. Billions, perhaps tens of billions of habitable planets. This meant more living worlds than there are people on Earth. This was the greatest paradigm shift in history. The question, are we alone, was becoming meaningless. Because the answer was a deafening no. The new question was, how many neighbors do we have? And what do they look like? These 50 planets were a sample space, and each one was a different experiment of life. Some were hydrogen-rich super-Earths like K2-18b. Others were smaller, rocky worlds orbiting red dwarfs. Some were ice worlds, their surfaces completely frozen, but harboring vast oceans under the ice. Webb's discovery proved that the galaxy is an incredible laboratory of life, each with its own unique conditions and evolutionary paths. The scientific community was, literally, shaken. Because this showed that life may not be a rare coincidence, but a fundamental feature of the universe, were found in abundance. This could mean only one thing. Something was continuously pumping these gases into the atmosphere, and just as life on Earth maintains the balance of oxygen and methane, this was evidence of a metabolism on a planetary scale. The breathing of a biosphere. The 99.7% certainty of dimethyl sulfide was the brightest jewel at the center of this picture. But the abundance of methane and the absence of ammonia were the vital pieces that completed this image. This was the first time in history we had such a strong, multi-layered line of evidence that an exoplanet's atmosphere was being actively shaped by biological processes. This wasn't just saying there might be life there. This was saying life there is changing the chemistry of the entire planet. And now, we go back to where it all began. The temperature, 49 degrees Celsius. This number, Shastis, might be the biggest miracle in this story, because this temperature is too perfect to be a coincidence. K2-18b orbits very close to its star. It completes a tour in just 33 days. This is even closer than Mercury's orbit around the Sun. Normally, a planet this close should have been scorched and turned into a hellscape. But it wasn't, because its star was a red dwarf. It was much cooler and fainter than the Sun. The combination of these two factors, a close orbit and a cool star, made the amount of energy K2-18 Be receives per square meter almost identical to the energy Earth receives from the Sun. This cosmic lottery was a miracle in itself, but what was truly incredible was that this temperature remained constant all over the planet. It has a tidally locked rotation. One side is constantly bright, the other side is constantly dark, and therefore, the day side was expected to be scorching, and the night side was expected to be frozen. But Webb's data showed that the planet's thick hydrogen atmosphere distributed heat so efficiently that there was almost no temperature difference between the day and night sides. This meant a planet with a global thermostat. This was a natural engineering marvel that seemed designed for life in the universe. And this was the first time in history that such a stable and homogeneous global climate had been proven on an exoplanet. Yet, the biggest shock perhaps came from the most unexpected place, from the C Antliae system, because when Webb looked there, it didn't see a mature planet like K2-18b. It saw a baby, a planetary system still in its formation. Stage only 6 million years old, and inside that system's debris disk, it found a planet candidate, the massive Saturn, with a surface temperature of again 49 degrees. This finding changed everything, because it showed that conditions suitable for life could emerge even in the chaotic and violent moments of planetary birth. A planet didn't have to wait billions of years to become habitable. Perhaps life was born along with the planet. The three-ringed debris disk around C Antliae was like a textbook showing the different stages of planet formation. And in one of those gaps, that faint glow, the evidence of a planet's existence, showed us how planets shaped their systems. But, most importantly, was that even this young planet had that magical temperature of 49 degrees. This implied that this temperature might not be a coincidence in the universe, but perhaps a fundamental set point on the path to habitability. This was the first time in history that habitable conditions had been detected on a planet in its formation stage. And this was the strongest evidence that new cradles of life might be being born right now. All across the galaxy, a giant mass, a living chemistry, a perfect temperature, and the moment of life's birth. These four epic discoveries, Alachi, when brought together, changed our view of the universe forever. We now see not just distant worlds, but their inner workings, their chemistry, and their potential biology. We are not just finding a planet, we are uncovering the potential of an ecosystem. But all these findings bring us to an even deeper question. Is the story of K2-18 unique in this universe? Or is this just the beginning? The data Webb has collected so far shows that similar worlds may exist in every corner of our galaxy, and the diversity of these worlds pushes the limits of our imagination. Because Webb didn't just find a planet, it opened the door to a new universe of possibilities. And behind that door, there wasn't just K2-18RB, there was a whole galaxy full of living worlds. Because Webb's revolution was not limited to a single planet. It was a statistical explosion. The telescope within a small sphere of just 200 light-years around Earth detected more than 50 potentially habitable planets. More than 50. This number alone created an earthquake. But because This meant that every corner of our galaxy was filled with life-bearing worlds. This was not an exception. This was a rule. The universe, yet, loves life. This is not an exaggeration. This is mathematics itself. If there are more than 50 candidates in just our tiny local neighborhood, a cosmic stone's throw of 200 light-years, then how many worlds could there be in the entire Milky Way galaxy? 400 billion stars. Billions, perhaps tens of billions of habitable planets. This meant more living worlds than there are people on Earth. This was the greatest paradigm shift in history. The question, "Are we alone?" was becoming meaningless, because the answer was a deafening no. The new question was, how many neighbors do we have? And what do they look like? These 50 planets were a sample space, and each one was a different experiment of life. Some were hydrogen-rich super-Earths like K218b. Others were smaller, rocky worlds orbiting red dwarfs. Some were ice worlds, their surfaces completely frozen, but harboring vast oceans under the ice. Webb's discovery proved that the galaxy is an incredible laboratory of life, each with its own unique conditions and evolutionary paths. The scientific community was, literally, shaken, because this showed that life may not be a rare coincidence, but a fundamental feature of the universe. But Webb's most epic discovery was perhaps its most abstract: water itself, but not the water we know. The oceans of K2-18b, because the size of these oceans boggles the mind. Models show that the oceans on this planet could reach depths of hundreds of kilometers. Hundreds. The deepest point on Earth, the Mariana Trench, is only 11 kilometers deep. The oceans of K2-18b could hold thousands of times more water than all of Earth's oceans combined. This is not a water world. This is a water universe. This was the first time in history that evidence of such a massive liquid water reservoir was found outside the solar system. This meant an unimaginably large space for evolution to play in. Life in Earth's oceans is concentrated in just a thin surface layer. But in an ocean hundreds of kilometers deep, unimaginable ecosystems could have developed in different layers of pressure and temperature. But the real revolution was in the chemistry of this water. Because this was not pure water. This was water saturated with hydrogen. This incredibly expanded the freezing and boiling points of water. This water could remain liquid even at 149 degrees Celsius. This meant that the conditions where life could exist were much broader than we previously thought. For the scientific world, this was rewriting the rules of the game, because it proved that just searching for water was not enough, that the chemistry of the water and the gases dissolved in it were at least as important as the water itself. And now, we come to that initial spark at the heart of everything, the methane mystery. Because there shouldn't have been methane in the atmosphere of K2-18b. This simple molecule, Yatsur, breaks down in just a few decades under ultraviolet radiation. But Webb detected massive amounts of methane in the atmosphere. This meant something was constantly producing it, and in unbelievable quantities. On Earth, the overwhelming majority of methane is produced by biological processes. But the methane concentrations on K2-18b were many times greater than what all biological sources on Earth could produce. This meant the planet's biosphere could be much more efficient and productive than ours. This wasn't just saying life exists. This was saying life is booming here. But there was a deeper layer to the methane mystery. Because this methane existed in a hydrogen-filled atmosphere. This raised the possibility of a biochemistry that does not exist on Earth. Organisms there could be breathing hydrogen instead of oxygen and metabolizing methane as an energy source. This was the first time in history we had such strong evidence for the potential existence of methanogen life forms on an exoplanet. This meant that the tree of life might have completely alien branches that we never knew. Scientists were both excited and terrified by this possibility. Because it meant we had to redefine the definition of life. More than 50 neighbors, oceans thousands of times larger than Earth's, and a potential biosphere that breathes methane. These epic discoveries, when brought together, tell us one thing. The universe is far more alive, more diverse, and more surprising than we ever imagined. Webb didn't just show us new worlds, it opened the door to a new universe of possibilities. But now, it's time to slow down from this dizzying pace for a moment, to stop and breathe, and to ask the most fundamental, most human question of all these discoveries. So, what does all this mean for us? How will knowing that we are no longer a lonely island in a cosmic ocean change us as a species? Because these discoveries are not just scientific data, they are our mirror. A mirror that makes us question who we are and what our place is in this vast living cosmos. And what we see when we look into that mirror, is a reflection that both diminishes and elevates us. Now is the time to stop and think, to step back from the dizzying speed of these discoveries and ask the most fundamental, most human question. What does all of this mean for us? How will knowing that we are no longer a lonely island in a cosmic ocean change us as a species? Because these discoveries are not just scientific data. They are our mirror. A mirror that makes us question who we are and what our place is in this vast whole living cosmos. Now, let's look deeper into that mirror. The first thing we confront, is a massive paradox of scale. On one hand, there is a literally infinite universe that James Webb has shown us, K218b, 120 light-years away, debris disks millions of kilometers wide, 400 billion stars in our galaxy, and billions of potential homes for life. On the other hand, there is us, one of the smallest actors on this immense stage. All of human history has taken place on a thin film of this planet, in the span of a cosmic blink. So how can such small and fragile beings witness a truth so much larger than themselves? This is both a tragic and a beautiful truth. Tragic, because it brings with it the overwhelming awareness of these distances. That 120 light-years, about 1.1 quadrillion kilometers, is a chasm we can never physically cross. It would take our fastest spacecraft more than 2 million years to get there. We will never set foot on those worlds. We will never swim in those oceans. We will never breathe under that sky. We are like prisoners, watching the most magnificent sights of the universe, but never able to touch them. This holds a deep sorrow, a sense of helplessness. But it is right at this point that a magnificent beauty is born from that tragedy. Because, even though we cannot physically reach them, we are there with our minds. Webb's golden mirrors become our eyes. Its spectrographs become our senses. From 1.5 million kilometers away, thanks to a machine operating in the cold of -233 degrees, we can decipher the secrets carried by photons that set out 120 years ago. This is the triumph of the human mind. Transcending its physical limits, we may be one of the smallest parts of the universe, but we are also the consciousness that understands it, that gives it meaning. You are at the very center of this paradox. You, in this 13.8 billion-year-old universe, are a being of about 1.7 meters, with an average lifespan of 80 years. But right now, through these words, you are thinking about the chemical reactions in the atmosphere of a world 120 light-years away. This is your power, your miracle. And this brings us to the second great contrast, the paradox of time. On one hand, there is the almost infinite lifespan of red dwarfs like the star of K2-18, which will shine for 10 trillion years. An unimaginable time frame for life to evolve. This is 700 times longer than the current age of the universe. On the other hand, there is our brief, instantaneous existence. All of recorded human history is about 5,000 years. This is nothing compared to the lifespan of that red dwarf. Not even a millionth of a second. So how can such ephemeral beings find clues about a future so much more infinite than themselves? The tragic part of this is confronting our own mortality. We live knowing that life on those worlds will continue even billions of years from now, but understanding that we will never witness that future. We are the audience of a cosmic play, who can only watch one act, but will never see the end. This creates a melancholy, because our story, no matter how important, is just a footnote in the grand epic of the universe. But, again with that magical word, but, this melancholy transforms into meaning. Because, yes, we are just a moment, but that moment is the moment that becomes aware of everything. We are the moment when the universe questions its own existence, thinks about its own past and future. Life on K2-18 Nephi may have existed for billions of years. But it is we who discovered the existence of that life, gave it a name, deciphered its chemistry, and told stories about it. This adds an invaluable worth to our momentary existence. We are the brief moment that gives meaning to eternity. You are inside that moment. You are not just an individual living in this time period. You are a part of the voice with which the universe says, "I am here," to itself. After billions of years of silence, your curiosity, your desire to learn, Horachi, is a reflection of the universe's effort to understand itself. And this brings us to the third, much, and perhaps most personal contrast, the paradox of loneliness and togetherness. On one hand, there is that old, deep feeling of cosmic loneliness that Webb's discoveries have ended. We now know that we are not alone in the universe. We know that the galaxy is filled with billions of worlds, each living its own biological adventure. The sky is no longer an empty darkness. It is a vibrant neighborhood, full of potential neighbors. This gives an incredible sense of relief and belonging. But on the other hand, there is a new and more complex type of loneliness that these discoveries bring. Because the distance between us and those worlds is not just physical, it is also semantic. We may never know what the life on those worlds looks like, what it thinks, what it feels. We may never have a conversation with them. This is a new kind of isolation, like being in a crowded room and not being able to talk to anyone. This is the reality that even after solving the universe's greatest secret, we may still remain lonely on a fundamental level. This is a painful truth. But within this painful truth lies humanity's greatest strength. Because even if we cannot form a universal bond, this shared quest connects us to each other more than ever before. We are no longer alone on this journey. As a species, we are all facing this new reality together. Scientists from different countries, from different cultures, are working together for this common goal. And you are a part of this togetherness. By learning about these discoveries, by talking about them, by sharing this excitement, you become one of the billions of people building humanity's new cosmic consciousness. Perhaps Webb's greatest discovery is not life in space. Perhaps the greatest discovery is how much that search can bring us closer to each other, here on Earth. Scale, time, and loneliness. These three great paradoxes are the fundamental pillars of the new universe that Webb has presented to us. They both diminish and elevate us. They both sadden and give us hope. But this philosophical journey does not end here. Because these discoveries not only make us question our place, they also make us question our responsibilities. Now that we know we are part of this living universe, what is our duty? What will we do with this knowledge? Because these discoveries are not just holding up a mirror to us, they are also handing us a compass, and the direction that compass points, and the direction that compass points leads us to the fourth great contrast, the paradox of knowledge and ignorance. On one hand, we know more than at any other time in human history. Thanks to Webb, we can detect a molecule in a planet's atmosphere at a concentration of 1 part per billion. We can measure the temperature of a world 120 light-years away with a margin of error of just a few degrees. We can look closer to the beginning of the universe than ever before. Our knowledge has exploded like a supernova. And our understanding of the universe has expanded irrevocably. But, on the other hand, each piece of this knowledge opens the door to a vast ocean of ignorance, showing us just how little we actually know. We know of the existence of dimethyl sulfide, but we do not know what the life that produces it looks like. We know of the perfect temperature of 49 degrees. But we cannot even imagine the complexity of the ecosystems that thrive in that temperature. We know of the existence of hydrogen oceans, but we will never see what swims in the dark depths of those oceans. Every answer gives birth to 1,000 new questions, and this reveals one of the most tragic and most beautiful aspects of being human. Tragic, because our quest for knowledge will never end. Like the horizon, it will recede as we approach it. Each discovery will be a painful reminder of how much larger the universe of things we don't know is compared to what we do. But this is also beautiful, because this infinite ignorance is our greatest fuel. It is what pushes us forward, what ignites our curiosity, what causes us to build new telescopes, to develop new theories. It is not the hope of reaching the end of knowledge, but the joy we take from the journey itself. You are on this journey. With every new piece of information you learn, you realize how much more there is that you don't know. But this doesn't stop you. On the contrary, it motivates you to learn more, because you share the universe's most fundamental drive, the desire to understand. And this brings us to perhaps the most unsettling contrast, the paradox of creation and destruction. On one hand, there is an incredibly fertile universe that Webb shows us, constantly creating new worlds. The debris disks around young stars like C Antliae are the cosmic cradles where planets are born. In these systems might, even now, the future K218b's, the future Earths, are taking shape. The universe is like a giant factory, relentlessly producing new potentials for life. Every second, new stars are born. Every moment, new planets are formed. And this gives an incredible sense of hope and vitality. Because life is not just an event in the past, it is an ongoing process, happening right now, all across the galaxy. But on the other hand, there is the cruel and destructive face of the same universe. Our sun will turn into a red giant in about 5 billion years and swallow the Earth, destroying everything on it. Sudden flares from red dwarf stars can instantly sterilize the planets in their orbits. Supernova explosions can destroy everything within thousands of light years. The universe destroys as mercilessly as it creates generously. This is a tragic truth that shows how fragile and coincidental our existence is. We are a spark, shining for a brief moment, between two annihilations. But within this fragility lies the incredible beauty of being. Because, yes, our existence is temporary, but we exist. We have had the chance to emerge from billions of years of cosmic possibilities and experience this moment, this consciousness. We are a rare and precious anomaly, dancing on that thin line between creation and destruction. This helps us understand how priceless every moment, every breath, every thought is. You are part of this dance. You are a being who both knows they will one day cease to exist and understands the value of every moment they do. Your existence is the most concrete proof of the universe's both creative and destructive power. And this makes you both humble and unique. Standing in the midst of these discoveries, one feels two opposing emotions at the same time. On one hand, that deep sense of awe and smallness we feel in the face of the universe's unbelievable size and complexity, feeling like a grain of sand in a giant ocean, meaningless and ineffectual. On the other hand, that incredible pride and wonder we feel at the power of the human mind, which can solve these secrets, the ability of that grain of sand to understand the ocean itself. Both feelings are valid. Both are true. Because we are both a grain of sand and the consciousness that understands the ocean. This duality is the definition of being human. As we try to find our place in this new cosmic reality, we need to embrace both of these feelings. We must feel humbled as a part of the universe, and also take pride in our ability to understand it. Because this balance will be our greatest strength, knowledge giving birth to ignorance, creation dancing with destruction, and humanity being both small and great. These philosophical reflections are just the beginning of the new era Webb has opened for us. We now know that the universe is not just made of rocks, gases, and void. It is a living, breathing, constantly changing and self-discovering organism. And we are a thinking, feeling, and meaning-seeking part of that organism. As this chapter of our journey ends, the questions in our minds are far more numerous than the answers. But we are no longer afraid to ask these questions, because we now know we are not alone. This is not an end. This is just the end of the story's introduction. And as far as now, with this entire load of information and emotion, it is time to stop one last time and think about what this new reality is telling us, what our next step as a species should be, because the universe has spoken to us, and now it is our turn. On this journey, we have seen that the universe is full of life. But there is something I haven't told you. All this life is threatened by an invisible force trying to destroy it. Dark energy, which is tearing the fabric of the universe from within, pulling galaxies apart, and will ultimately tear everything to pieces. On our next journey, we will hunt down this cosmic killer. Are you ready?